Greetings, statisticians. 2.5 measures of variation. So this is just my introduction to what's coming here in section 2.5, and then tie it off with 2.4. Basically, measure variation, for the most part here, like this first sentence, we're going to call it the standard deviation. And that's another way to express variation of data, and that's exactly what that is. Go back and refer to the example that I did with comparing the mean to the median with the outlier of the wage earner of 5 million versus 30,000. And so an example like that, where the mean was reported as $129,400, but the median was 30,000. So obviously there was a big difference between those measures of center. What set that off was the outlier. And I said that outliers really throw off variation, in this case standard deviation as well. So coming down here talking about this thing, unusual values or those outliers kind of makes variation vary more. So it's not just a thing to look at the center, but also make a judgment of variation as well. So suppose that we have Class A and Class B. Class A has a 72%, Class B has something really close to it, and then one could say that, oh, they scored about the same, therefore their performance was identical as well, and that's certainly not true. It's not enough to look at just the center, but also the variation of data. Once you start comparing the variation of data, then it can make the list stand out completely different. So as I go through examples here, I want to go through and show you where the mean, median, mode, min-range, all of those numbers were the same, well, except for the min-range. All those numbers were identical, but the variation of the data were so different. So be careful. We can't imply that two populations are the same based upon their average. Certainly the next thing to add to that is variation of data. And so building up these concepts, if you look at the definition of the mean a little closer, it's called expected value, and we'll look at expected value in chapter 4. But mathematical expectation, or what we call moments in physics, defines these different types of measures here of a sample. So in a couple ways that physics does play out a way of affecting statistics in a good way, like the formula that we use for finding the center of mass is kind of used here in statistics. And they're called moments, and if you want to look that up, Mr. Burrell criticized me for using, talking about moments and moment generating functions. It's kind of an inside joke now. But basically moments look at measuring variation of data, measuring center, and even beyond that, kurtosis and those sort of factors that look at data, that tell a different story about data than just the graph. The graph is where we want to start, but eventually we want to get into further analysis with it and have the numbers speak for themselves. But of course, if we have a biased survey and biased data, none of this really matters anyway. Coming down here towards the bottom of this, I look at this definition here called deviation, and it's in this perspective here. This is the data value, the data minus the mean. We're going to always go in that direction. That's defined as deviation up here. So deviation is important, and repeatedly look at the distance from the mean. For scatter plots, whatever it is here, that distance is what judges variation of data from what? From the center. So think about that way. We want to see how our data varies from the mean or the center. Now we could use any type of center of measure. We could use the mode, the min range, but we use the mean because it's the most arithmetic in its calculation. So there are other formulas that use something different than the mean, like let's say the median. Coming down here at the bottom, we look at that deviation here. This is from a sample perspective, but again, there's two types of formulas. I'll go over their symbols at the bottom. Here for the first one is called the population variance. And the population variance is kind of telling a story here with regards to the order of operations. Inside the parentheses first, if you know that PEMDAS, And that's basically parentheses, exponents, multiplication to division left to right, or addition, subtraction left to right. So parentheses first, that we want to do this first, and of course the deviation. Figure out that distance is from the mean. Then we're going to raise that to the second power. Then we're going to add those all up. So for each individual data, you want to do that point. How far is each one of those data points from the mean, and then raise the second power. And we'll see here why we want to square it is because we would want to ignore all negative factors, that that if it's negative, it indicates that it's a deviation below the mean, and if the deviation is positive, the data value is above the mean. We square that to try to negate the deviations, and I'll point that out why we want to do that. Another perspective you could take instead of raising to the second power is also applying the square root, or sorry, the absolute value, and it kind of does a similar thing there too. And then finally, when you're done, you divide by n, and that uppercase n there stands for the population size. That's the formula for the population variance. But if we, and of course down here I'm going to present the symbol for that. This is called sigma squared. And sigma, lowercase sigma, stands for S there, and essentially going to get down this word called a standard deviation. But it's a squared number because these are all squared numbers, particularly if you look at, because we're squaring the deviation, the symbol for it is raised to the second power. So realize that all variance or variance statistics are average square values. If we come back over here for the sample, we're kind of doing the same thing. We're looking at that distance from the mean. That's the deviation. Raise it to the second power. Do that for each data value and add those all up. And then slightly different here, we're going to take that total and divide that by n minus 1. And there's a reason for that. I'll probably point that out later, but it has to do with what's called an unbiased estimator. So if it's for, so basically what we want to consider right now is that if it's for a population, divide by the number of data values in the population set, in other words, the population size. But if it's a sample, you want to do that too, but then take one away from the sample size and then do your division. So a little caution here, this is only true, this is not true for the sample mean, this is only true for the sample variance. And the symbol for that is S squared. And typically in statistics that we take letters of the alphabet and express them for stats. But if there are letters from the Greek alphabet, and I have that in the notes in section 2.4, those are representative of population parameters. And then down here summarizing this at the bottom, anytime you want to find a standard deviation, you always want to take the square root of variance. And so in regards that either form of variance is a squared number, doing the opposite of raising to the second power is the square root, and that brings it back to our original deviation there. That's why it's called a standard deviation. And again, I'll point that out in the first example. So this is just an overview of this topic here, and then down here at the bottom, I have the different symbols you want to look for. Again, basically coming from our alphabet is our stat symbols. So stat symbols. And then over here is our parameter symbols. So basically those are letters from either the alphabet or the Greek alphabet there that represent their definition here on the side here. So size, you can look at in one of two ways. That size could implement, you could say that either you're going to use the lowercase n or the uppercase n. So the lowercase n is for the sample size, uppercase would imply for the population. Down here for the mean, we have two symbols for it. If you use x bar, you're indicating that's a sample mean. If you use a symbol mu, that is for the population mean. Coming down there further for the topic here in 2.5, if you use s squared, that's a symbol standing for the sample variance. So in some ways, it's easier to write out s squared than it'd be to spell out the words sample variance. Coming right next door over there for the parameter, so sigma squared is a symbol for population variance. Again, it's easier to use the symbol rather than writing out the words population variance. The last one down here at the bottom is our sample and population standard deviation. So if you take the square root of s squared, you get s, and s is a symbol for the sample standard deviation. And for the parameter, sigma, alone is a symbol for the population standard deviation. So we use symbols a lot here to emphasize for those a shorthand notation. I'll use it when I'm texting someone, like instead of writing out be right back, you just put BRB. Or if I write back to you and say no problem, I'll just skip that and I'll write NP. So that's, you know, short abbreviation for spelling common. Text in texting or mailing is pretty common to do that. Shorthand, we do it all the time, particularly here in mathematics. We do it a lot because it's easier to write out the symbol than it is to state a sentence like that. Let me just show you here briefly, like in analysis, like real analysis here. I do this like every semester. So in a way that math is its own language. So I'm saying that a sequence approaches a limit, and that's if and only if for every epsilon greater than 0. So in other words, you want to pick any epsilon that's greater than 0. And the idea of epsilon is super small, but you can always find that there exists a delta, or sorry here, an x value, or okay, let me back up for a sequence. A lowercase n, you can find a lowercase n greater or equal to uppercase n. That may be strictly greater than. I have to go look back in my books again there, crack open the books. That would imply that the distance of a sub n from a is less than epsilon. So here in this statement, I'm saying that even though it looks like it's all in Greek, there really isn't. And so it, to us as mathematicians, like if you go pull up a book that's in German, or I don't even know, like any, it doesn't matter, any national, or I don't know, country or whatever that to write mathematics, this language is universal here. So again, that these symbols here express convergence, and I'm saying that we have a convergent sequence if this is true and vice versa. So if we have, for any epsilon greater than 0, you can always find an n that exists such that that gap is less than epsilon. And that's how we define convergence for a sequence. So I'm saying that even though those are all symbols, this is how we communicate in mathematics. So on a lighter note, I'm going to have you folks just know some symbols here and the English interpretation of that. But as far as you go a little more advanced mathematics, like a real analysis, complex analysis, even undergraduate algebra or graduate level algebra, we don't really have much numbers in there. You know, I think in this thing, the only number that exists is the number 0, even though the rest of them are numbers in that case. So we use a lot of Greek, I guess, and we talk a different language. And it's fun. It takes a while to learn the language, which I hope like I could convince universities that, yeah, I speak math and I wouldn't have to take a foreign language there. So there's my little intro of what's coming here in section 2.5, talking further about measures of center. That it's okay to find the center number, but then you got to take it a step further and find the variance and standard deviation.